So today's class will be only thermodynamics.
Yeah, we'll finish off thermodynamics, last part of it. Before we start talking about entropy, so we've done all about enthalpy, right? So we figured enthalpy is basically the energy. It's the sum of the internal energy plus the pressure volume product, work product. So all encompassing is enthalpy. And whatever energy changes we talk about, be it ionization energy, electron gain energy, exothermic, endothermic, may we say energy is absorbed, energy is released. We are specifically talking about the enthalpy in this situation. Okay. So enthalpy, okay. So yeah, energy is released in some reactions, energy is absorbed in another reaction. Sometimes the net delta H is also zero. Okay, so this is what we've seen so far. Let's talk about spontaneous processes. What do you mean by spontaneity?
Suddenness.
Sudden? Okay.
Instantaneous.
Like instantaneous.
Kinda, correct. What would you associate spontaneity with? Like, what sort of sense does it give you?
Something that doesn't require preparation.
I think like as soon as you do the reaction, you get it immediately.
Don't think about it in chemistry and all, because we just started discussing about it. Generally, spontaneous ka matlab, what do you think? Like what sort of
fast, immediate things.
Like on the spot.
On the spot, spontaneously, yes. Ritu has mentioned one more thing where you don't need like prior preparation and all. Yes. All of this together, absolutely. So even in chemistry, spontaneous process ka matlab is exactly what you think of it. Okay. So it's not like just one small difference. It's not something instantaneous. It's more in the thing of more on the lines of you don't need to force it to happen. It's going to happen on its own. Yeah. So that's a spontaneous process. So something that happens on its own instantaneously, not like in terms of time ki ek second mein ho jayega, but you don't have to spend energy for it to happen. You don't have to force it to happen. Other words you can use for it are feasible process. Something is feasible matlab you don't have to work hard at making it happen. Like it happens on its own. Something that is able to happen. Probable process. Okay. Can you, like, considering these examples, can you give me some, I'll give you an example of spontaneous process and then you guys can take it from there. Let's say I have an inclined plane and then I put a ball over here, like something spherical, round, cylindrical or spherical. So the ball rolling down, that's a spontaneous process because you don't have to push it. You don't have to do anything. You don't have to put a motor in it. If it's an inclined plane, if you have like ball at a height, if you have any object at a height, it's gonna fall. Like that's natural, right? You don't have to do anything special to make it happen. So that's an example of spontaneous process. So similarly, can you think of some other spontaneous process that you might have come across, you might have done, you might have observed in nature?
Melting of ice in room temperature.
That's nice. Excellent. You don't have to do anything. It automatically happens. Melting of ice, yes. At room temperature specifically, yes. Ritu said
Clothes
example.
dry when
Huh?
kept in the sun.
Sanat, what is kept in the sun?
Like wet clothes, they dry when kept in the sun.
Evaporation, basically, right? So evaporation is spontaneous. Yes. Ritu gave
Is
an
like
example of forest fire. Yeah, Adit.
is like when you don't apply like a zinc or lead to an iron, it will rust it like on its own. Like you can't
Yes.
do anything about it. Does
Rusting
that
is
count?
spontaneous. Oxidation of iron is spontaneous. Correct.
Evaporation, like the from naphthalene balls, basically, it's directly.
Sublimation of naphthalene at room
Yeah.
temperature. Yeah, that is spontaneous. Correct. Yeah, Kaveri, you were mentioning something.
I don't remember the exact reaction, but I think it was like iron and maybe I think cold water or something. And then it like we watched this experiment and it just like set itself on fire.
Right. Certain experiments like that. Yes. So some reactions are spontaneous because you don't really need any trigger for it. Absolutely. What about putting salt in water? So when salt dissolves in water, is that spontaneous? Would you call it spontaneous?
Yes.
Yeah.
Yes.
Absolutely. What about burning? Yes,
Ma'am, can photosynthesis be considered a
photosynthesis.
small?
That would be difficult because you guys have just studied about
You need
photosynthesis.
light energy for it, right?
You need light energy, yes, but like photosynthesis itself is a combination of multiple smaller steps. So if anyone would have taken bio, you would study about it. I don't know, you have Krebs. I don't know if Krebs cycle is part of photosynthesis or respiration, but you have like light reactions, dark reactions. It's a whole process. So I don't know the details of what steps there are, but some steps would be spontaneous, some of them would not. So that's difficult to classify. What about lighting a candle flame? Would you call it, or just lighting a paper on fire? Would you call it spontaneous?
Because we are providing energy.
No, we are providing.
So we are still providing the external factor, that is the matches or whatever we are using.
Mm-hmm. Do you have to continuously put the march over there, like on paper for it
Oh,
to?
just once. Just have to make contact
Oh
with
no.
it.
You just have to make contact with it. After that, it still happens on its own, right? So that also would be considered as a spontaneous process. Like you shouldn't have to force it to happen. Like a tiny little trigger, like you just provide that, so that energy is called activation energy. We talk about it in next like 12th May chemical kinetics May. So you just like push it, like do a little bit of thing, and then it happens on its own. So even that is a spontaneous process. Okay. So everything that happens naturally, that happens on its own without providing any help for that process to happen, is a spontaneous process. Initially you may provide a little bit of a trigger, but as long as that trigger is not required throughout the process, it would be spontaneous. Like for example, if I were to lift this like from the bottom to the top, it's not like I just push it and then it happens, right? Like I need to keep pushing it, work against gravity all the way till here. So that's not spontaneous. But falling, if I just leave it, it just happens on its own. So that's like the difference between spontaneous versus non-spontaneous processes. Okay. So
Ma'am,
yeah,
so breaking of glass would be considered spontaneous or not?
breaking of glass, not, again, it depends on temperature, pressure, because if I just have a glass bottle, glass exists, right? It's not like I create glass and then it just
But
breaks.
ma'am, glass is fragile, right?
No, like if we just drop it and it breaks, so is it spontaneous or is it not? That's like the question.
that would be spontaneous, because it's not like you need to keep, again, it depends on the type of glass and everything. If it's like something fragile, you don't have to keep chipping away at it for it to break, right? Like you provide that one small disturbance and then the crack just goes all the way. So then it would be spontaneous.
Okay. Yes.
So something that, you either leave it like that or just give it a little bit of a push in order for it to overcome that initial activation energy and then leave it. So if you're just leaving it at any point and then it's happening on its own, it's spontaneous. But if you have to continuously provide some sort of a catalyst, some sort of energy, electricity, anything like that, then it would be non-spontaneous. You don't have to keep pushing at it. Now, why do spontaneous processes happen? Like, what is the major, so you can identify what is a spontaneous process versus what is not a spontaneous process. But why do we have, like, specifically, some process happening spontaneously and the others not? Okay, let's take chemical reactions, for example. Okay, in terms of chemical reactions, you have exothermic reactions and endothermic reactions, right? Or in general, like, let's say, suppose I have a hydrogen atom and another hydrogen atom. Individual atoms are not capable of existing. You will never find them. Maybe they'll exist for like a fraction of a second during a reaction, but you will never find them independent like this unless they're like noble gases or something. They will always combine to form. Like, that's why when you do electrolysis also, cations, anions split up, but when they go towards cathode anode, they always, join back into other products and then they are released. Like, they never exist as atoms. Why is that the case? Like, why are compounds formed? Why are molecules formed?
To gain stability.
Stability, absolutely. And what do you mean by stability? Like, when we look at it in terms of like quantitative like criteria, like numerically, if we have to measure, Kaveri said yes, octet, absolutely, octet means stability. But quantitatively, what does it mean? Octet, fully filled last shells, absolutely, all of these mean the same thing, stability. But in terms of energy or enthalpy, like in these terms of like physical measurements, like in terms of the properties that you can measure, what does stability mean?
The one that is least reacted,
Huh?
the one which is less reacting. I mean, they don't react very easily. So the energy of it might be less because then it cannot react.
That phrase that you mentioned, Rishit, that was what I was looking for. This is something I mentioned at the start of, at the absolute start of the whole of chemistry, actually. Ritu also mentioned a point, bonding versus anti-bonding. What is the difference between bonding orbitals and anti-bonding orbitals? Like, why are anti-bonding unstable but bonding stable? So stability is basically associated with lower energy. That is why electrons also prefer always occupying the lowest possible energy state first, and then if they don't have a choice, then they'll go to the higher thing. So any substance, be it electrons, atoms, molecules, anything in the universe, like even humans for that matter, if you had an option between being in a higher energy state versus lower energy state, What would you prefer? If I gave you option of just run 5 kilometers every day for 3 hours versus chill, like just stay
Lower energy state.
lower energy state. It's the same with atoms, molecules, chemicals also. Stability means lower energy state. Even the difference between bonding, anti-bonding, those orbitals, bonding orbitals are at a lower energy state, which is why bonding is more stable. That's why they are occupied first. Anti-bonding is higher energy state. Always, always, always lower energy state. So tying this back with spontaneous process, like why do spontaneous processes happen? Because the overall energy of that particular system is decreasing. So initially it was at a higher energy, uske baad it's going at a lower energy, which is why the system prefers that process to happen, and then it's happening spontaneously on its own. So that explains exothermic reactions. That's pretty obvious. In the case of exothermic reactions, so delta H, overall enthalpy less than 0, it's a negative value, which means that overall enthalpy, basically your energy of the system is decreasing. Isliye exothermic reactions happen spontaneously. That's why combustion happens spontaneously. You might need something to activate it, but once you give that little bit of path, it's like a chain reaction. It's gonna, all the molecules keep bumping into each other, combustion happens, and you have that fire, that flame, energy is released. But what about endothermic reactions?
Delta H greater than 0.
Yeah, delta H greater than 0. Endothermic means you're adding energy into the system. Energy is absorbed by the system. So, but still some endothermic reactions are spontaneous. Why? How do you explain the spontaneity in this case? For that matter, there are some processes where delta H is equal to 0. So there are some reactions like hydrolysis of esters. You guys remember what esters are? ESTERS.
I have a small doubt.
Hmm.
So, when you talk about endothermic reactions, it also, I mean, evaporation itself is also an endothermic, right? It takes the heat. If you just keep it outside, that is an endothermic reaction.
If we keep what outside, which process are you talking about?
Water. If we just keep water outside in
Evaporation.
below the sun.
Yeah. Yeah, absolutely. Like water being evaporated is endothermic. That's why you have that cooling sensation and all that. Like water molecules absorb energy and then they escape into, like they become gases. That's an example of like not just
Like,
yeah, Ritu?
would endothermic be like they take in energy and then they like use it to become gases because their gas state is more stable?
No, because physically speaking, chemically speaking, like gases have more kinetic energy. So energy wise, it's not like gases have a lower energy state. If you look at the chemical stability, like chemically, water has not changed. Jo octet tha, whatever configuration of the molecules is there, that has not changed from liquid water to gaseous water. So that way also there is no change in the stability factor of it.
So, ma'am, does this also explain like how deodorants and perfumes also work?
Diffusion of gases, yes. Deodorants, sublimation, yeah.
Like
all-
you mentioned esters, that's why I wanted to ask.
Oh, esters specifically? No, I'm talking about esters ke chemical reactions. Okay, you guys remember that esters are used for perfumes. Okay, cool. Do you guys, wait, you did your 10th standard during lockdown, right? Did you guys do the like reactions of acids and carbon compounds chapter?
No,
No, ma'am. We only did the nomenclature, I think. Uske baad was deleted.
Oh,
Like the washing.
yeah. Then you couldn't know about esters. Okay. So esters are basically compounds formed from acid and alcohol ke reaction. So uska reverse reaction also is feasible because in that case delta H is equal to 0. Like this is the reaction, okay, just for your information, I'll just give you. CH3COH acetic acid plus alcohol, let's say C2H5OH. So in this, the OH from the acid group and H from the alcohol gets eliminated to give you another compound. So CH3, CO from the acid bonds to the rest of the part from the alcohol. That's water. So this process delta H is technically 0. Iska reverse is basically hydrolysis of esters. So yeah. Rishit, why did I write feasible and probable? So these are like other names that you can call spontaneous processes by. You also call them feasible processes because they are feasible. They can happen. It's not like you have to spend intense amount of energy and like work to be done for them to happen. They're probable because, like nature is telling you that this process should happen. So it's likely that it will happen. So these are other names for it. So coming back to it, exothermic, we have an explanation, stability, lower energy. Exothermic may energy is decreasing, it's being released, so they can happen spontaneously. But what about endothermic reactions and processes where delta H equal to 0? Like diffusion, evaporation, these kind of reactions, like why are they spontaneous? So the reason, like you guys came really close to it, it is the difference between liquid state versus gaseous state, but it is not related to enthalpy. So there is another physical property of the universe, which is called entropy.
Ma'am, can you go back 1 second?
Yeah. So this is explained. This, how are they spontaneous? That's what we're looking at.
Done.
So in order to look at that, this is just like how we learned about internal energy, pressure, enthalpy, temperature. Entropy is another state function. It explains, like it is another characteristic that explains the state of any system, a substance, a beaker, a system, whatever. It is denoted by the letter S. It is a state function. Essentially, this is the measurement of chaos. If you had to have a physical measurement for chaos or disorderliness, that's entropy.
For spontaneous reaction of some process, writing feasible and probable is enough, right? Or we needed to write something else too.
That's fine. Like again, you just need to have an understanding of what a spontaneous process. Like you won't be asked for definition and all. There are better questions to ask from this chapter. Don't worry about it. If you want to go over it, yeah, just refer to like the textbooks or chapter notes. Focus on the understanding of it. All right. Coming back to entropy, so if you want to figure out why certain processes are spontaneous, along with enthalpy, you also need to consider the entropy of the situation. Entropy is basically another word. It is the measurement for disorderliness. So something is more chaotic matlab that system has more entropy. Something is less chaotic, it means that it has less entropy. That's all it is. It's a word that describes, that gives you mathematically how chaotic something is. Just like how you have length, 3 meters, 5 meters, 3 centimeters to show you how long something is. That way, entropy is the physical measurement for how chaotic something is. Yeah. So why do we need entropy? Okay, so let's discuss a little bit about entropy. If you consider solid, liquid, gas, what can you say about the entropy between the three phases? Do they all have, like, if you're considering the same substance, like ice versus water versus steam, do they all have the same entropy, or do you think the entropy of all of them will be different?
Gas would be the
Okay.
most chaotic, like the most entropic entropy, followed by liquid, then solid.
Yeah. Everyone agrees? Like, do you guys get it? How, why?
Yes,
Yes.
ma'am.
So gases have maximum entropy, followed by liquids, followed by solids. The reason is, again, it's very, very basic. Solids are rigid, they're all orderly. Liquids slightly better than solids, like they're still together, but there's this thing. But gases, they're the most disorderly of all, like all the molecules, like they just move around everywhere. So gases have maximum entropy compared to solids, lowest entropy, lowest S. Okay. So this kind of explains. Acha, before we get there, a few more this thing. Another thing about entropy is higher mass, like if you compare different gases with different masses, the gas that has a higher molecular or atomic mass, basically if it's a bigger atom or a molecule, then that means it has higher entropy.
How are entropy and spontaneity related?
I'll tell you. So they are related by the second law of thermodynamics. So I'll get there. We'll talk about entropy a little bit, and then I'll tell how they're this thing. Similarly, if you're comparing with similar masses, like gases with greater number of bonds, means they would have higher entropy.
I didn't understand how higher mass will mean higher entropy.
Higher mass, like, so as the think of it this way, like if a molecule is bigger or an atom is bigger, like let's compare, like for example, neon versus entropy of radon or xenon. Both of these are inert gases. Out of these two, kiske particles will have more amount of energy, kinetic energy?
Outer?
Between neon and xenon, which particles do you think would have more kinetic energy?
Xenon?
Xenon.
Xenon, H-omega.
Yeah, half mv square. Yeah, at the same temperature, if they have similar velocity, xenon's gonna have like higher kinetic energy, which means more energy means they can move around more. Think of it that way. It's just a property, like higher entropy, like higher mass, bigger molecules means they would have higher entropy. So as you go down in the periodic table, like if you're comparing fluorine versus iodine, iodine has greater entropy compared to fluorine.
So basically, higher mass would lead to greater kinetic energy, and that would lead to higher entropy.
I mean, it's not as simple as that. Like that is the property.
Okay.
Yeah. Similarly, like if you have greater number of bonds, like each of the chemical bonds would have its own energy, right? So there's potential for like there's potential for greater amount of energy. So greater number of bonds means higher entropy that way. Like where this makes sense is if you're comparing entropy of acetylene C2H2 versus entropy of ethene C2H4. So greater number of bonds, so this is gonna have a higher entropy. And these two will have lower than ethane, which has like C2H6, all single bonds. Also, another way you can look at it is if there's greater number of bonds, that also means there's greater number of atoms within that molecule. Which again ties in with higher mass and all of that. Yeah. Okay, another thing, how do you think entropy is related to temperature?
Higher the temperature, higher the entropy.
Yes, absolutely. Higher temperature also means higher entropy.
Could you go over the point about more bonds equal more entropy, like higher entropy? Could you go over that point again?
What exactly do you want me to go over it? Like basically, if you're comparing molecules, the molecule containing the more number of bonds, matlab, more number of bonds means it's going to have more number of atoms also. So that correlates to entropy as it's going to have higher entropy. Like for example, ethene is just this much. You have bond between carbon, hydrogen, carbon, 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 hydrogen. Versus if you take ethine, so ethene, it's got extra, like it's got 4 hydrogens. So apart from carbon carbon bond, you have 4 other bonds instead of just 2 other. So it's going to have more entropy. And compare that with ethane, which is bonded to 3 hydrogens each carbon. So it's going to have the highest entropy out of all. So basically, when you're comparing multiple different molecules, the molecules having like greater number of bonds or like more number of atoms, basically, if the atomicity is more, then that's going to have higher entropy. Think of it that way. Like if you're comparing entropy of one molecule or 1 mole of ethene versus ethine versus 1 mole of ethene versus 1 mole of ethane, ethane is going to have maximum entropy. Okay. So I'll take some specific cases and then you guys tell me, what do you think is happening to the entropy? Is it increasing, decreasing? What's going on there? Okay. Vaporization में is entropy increasing or decreasing?
I guess increasing.
Increasing.
Increasing. So vaporization is liquid to gas, no? So gas has more this thing. What about crystallization?
Decreasing.
Okay, Sanat is
Increasing.
Rishit also decreasing.
Decreasing because solid is formed.
Yes. Crystallization is basically liquid to solid ho raha hai. This is decreasing. What about sublimation?
Increasing.
Increasing.
Increase.
Very nice. Absolutely. Okay, these are all like general chemical processes. We'll take some real life thing. What happens when you boil an egg? Does entropy increase or decrease?
Decreases.
Decrease.
Decrease.
Oh, Ritu says increases.
Increase.
System here, the water or the egg?
I'm boiling an egg.
It will increase. Like that if
What
the egg
happens?
is being
Consider egg. Egg is my system, and then I'm increasing the temperature, like by putting it in boiling water or whatever. So what
The
happens?
liquid of the egg becomes solid, right? The egg boils. So
Hmm.
the
it will become
will
the
decrease.
liquid. It will become like a yolky thing and then
Hmm.
Will decrease because yeah, it's boiling and it's becoming solid. So
Correct. Yes. Yeah. So water we don't care about. Yeah, we are just looking at the egg. What happens if we are boiling it? So yeah, the two decreases. What other process do we have? Evaporation and all we've covered. What else? Stretching a rubber band.
It increases, then decreases.
क्यों? मतलब I'm just stretching it.
Increases.
Because like when you increases, wait, no, it'll be overall increase. Overall increase.
Yes, overall increases only. Like Sanat, why do you say it increases then decreases?
No, because I thought ki like you'd stretch it and then when you release it'll go back. So like it
Oh.
gets compressed.
No. I'm just stretching it. That's it. Stretching. I'm not releasing it. Just stretching.
Ah,
Repeat.
okay, then it's increase.
Yes.
If it was releasing, then it would decrease.
Yeah. Opposite process है. Entropy would opposite होगा. Yeah. This like stretching of rubber band, Ritu, it increases because like you guys did spring K problem, right? I'm basically inducing potential energy into it. So from the rubber band's point of view, I'm making it more chaotic. Basically, I'm adding energy into it. Like now this has like a potential energy induced into it. So this would be like entropy increases.
I have another doubt, ma'am.
Mm-hmm.
So then when you leave it, how would it decrease? Because that energy is converted into kinetic, right?
Yeah. So again, entropy is also related to energy. So there is a process. So there that conversion happens. So I'll get into it. Okay, so these are like some of the processes. You guys now have a clearer picture of entropy.
Yeah.
Yeah.
oh yes.
Okay. So this brings us to the second law of thermodynamics. Now, your question as to why we're talking about entropy, how is it related to spontaneous process, how it's related to spontaneity? Like this is what ties it together. So according to second law of thermodynamics, like if I were to put it in a layperson's words, the universe always favors increase of entropy. Okay. So always, like mass is conserved, energy is conserved, momentum is conserved, but entropy always tends to increase. Like the universe favors increasing entropy. This is where all your memes come from. I don't know if you guys have come across it, but why do earphones get tangled up always? Because of entropy. Favors disorderliness. And it's also, like one of those memes, like, why does your room get messy even though you keep arranging and everything? Because the universe favors disorderliness.
Ma'am,
Hmm.
but if a wire gets tangled, wouldn't the entropy decrease? Because they're all getting contracted, right?
There's no expansion or contraction. Initially it was orderly and then it's becoming disorderly. That's what's happening when things are getting tangled. Nothing scientific. It was just a meme vision, just a joke. Yeah.
Okay.
So put in formal terms, okay, I'm going to read out. Second law of thermodynamics can be stated as, so whenever a spontaneous process takes place, it is always accompanied by an increase in the total entropy of the universe. Okay. Or in other words, like if you were studying thermodynamics and physics, this is how it would be put as, it is impossible to take heat from a hotter reservoir and completely convert it into work by a cyclic process without transferring part of the heat to a cooler reservoir. So it's also called Kelvin statement. So basically, if there should be a spontaneous process, it is always accompanied by an increase in entropy. So that is the second law of thermodynamics.
Ma'am, is it possible for you to repeat? Is it possible for you to repeat?
Yeah, one sec. Here is the statement. So for a spontaneous process to happen, for a spontaneous change,
Ma'am, you're not sharing it.
sorry.
Are you sharing
You're
the
not
screen?
sharing
Like,
that.
thing?
Oh no, not sharing. I'll put it here. Wait.
Okay.
So when a spontaneous process takes place,
This is the statement for the second law of thermodynamics.
yeah, it is always accompanied by total increase in entropy of the universe. Yeah. So if you have a spontaneous process, something that happens all on its own, basically delta S should always be greater than 0 for a spontaneous process. So delta S of the universe basically is always greater than 0. Kaveri gave a very good question. So by that logic, shouldn't most matter have a random arrangement of particles? Absolutely. That's why you have evaporation. That's why you have sublimation. That's why it's random.
But ma'am,
Hmm?
like didn't we also see that everything else like happens in a balance, and like you see all these like things about everything being in like a Fibonacci sequence and stuff?
That's just pattern recognition. People have observed patterns and they have given, the rule of thirds and the golden ratio and all of that. Things
But
can.
won't that be in an order then?
So it's a so that's where we'll get into after this. So this is what second law of thermodynamics states. This is like an overarching thing. That's why I specified total entropy of the universe. So at some point, like if you're decreasing the entropy of the system itself, you are adding entropy into the surroundings somehow, or it is accompanied by conserving energy. Like energy should be lower. So overall, delta S of the whole universe of the system plus surroundings should increase. Like if it is not increasing for the system, it should be enough to increase the thing of the entropy of the surroundings. Like, so we'll get deeper into this. So yeah, once you're done noting the statement down, we'll talk about how it's related to enthalpy and like all the other things. So just, yeah, Sanat?
So like every time we perform a reaction, are we like increasing the entropy of the universe?
Yeah, yes. Entropy is always increasing.
Can we calculate like the total entropy of a substance?
Yeah, I mean, I told you it's a mathematical quantity denoted by S. How we are going to calculate
Alright.
it all? We'll discuss
What
that.
about the total entropy of the universe?
Total entropy. Okay, I haven't like delved that deep into it, but yeah, we can definitely check that out.
I don't think it'll be possible because like the universe is constantly expanding, right?
Yeah.
Wait, so in that case, won't it be constant because the universe is also expanding, the entropy is also increasing?
Hang on, I'm just doing a Google search. Second law of thermodynamics, the total entropy for an isolated system can never decrease. It should, for a process to be spontaneous, it should always increase. That is the main thing. Let's see, entropy of the universe. So someone has already Google searched this. Ritu said you had read somewhere that entropy was a probability. Again, entropy is not simply equal to probability, right? So need a little more context around it, Ritu. So where it is of significance, where it's really, really important in like real life when you're designing systems and sources of energy, like we talk about conservation of energy, we try to get it back into the system and all that. Have you guys ever heard of this thing called perpetual motion machine?
No, ma'am.
No? Okay.
No.
So theoretically, there was a proposal. So whatever, like suppose you're looking at generating energy, electrical energy. So you always, so energy can neither be like, you can't, it can't be lost or created, can't be destroyed or created, right? It's always conserved, right? Which means when you are producing electrical energy, you're always converting it into another form of energy. Like if you're thinking of dams, which is the most obvious example I can think of, you're converting the kinetic energy of water, like water falling from a height from over the dams, rotates turbines at the bottom. So you're converting mechanical energy, that is energy due to the motion, kinetic energy, like potential energy and kinetic energy of the water, into electrical energy by use of your generators, AC generators, DC generators, all of that. So okay, you have kinetic energy, you're transporting it into different places. We use that kind electrical energy into in lights, in fans, all of that. Now one can argue that can't we design machines in such a way that we use that electrical energy, harness it back again, and put it back into the system? Like think of, so like why can't we make it a cyclic process? So technically in a cyclic process, because you're getting back to your original state, However, you're getting there, you're getting back over here, right? Which means when all your variables are the same, your pressure, temperature, volume, enthalpy, work done, when all of it is back to point A, your overall energy also should be the same. So it makes sense theoretically, but practically speaking, because of the second law of thermodynamics, always states that there should be increase in the entropy of the system. So let's say you're increasing the entropy from getting from here to here, but when you're going back, when you're reversing the process, you technically can't decrease the entropy of that particular process, which means that you're losing some amount of energy there. So practically speaking, because of second law, you can never get back to your original situation because the entropy of the universe has changed by that point. So yeah, so this like a huge, it's like one of those unsolved problems in physics, like it's a concept, it's like a research concept that way. So you can never construct something called a perpetual motion machine. Yeah.
Ma'am, how do you, I know you will say it later, but how can there be a value to entropy?
Just like how you have a value for length, area, energy, just like that.
But like entropy is like you told this
That's
earlier.
measurable. How do you measure chaos?
So it's measured by S. So this is the formula for entropy, okay? How mathematically, how do you measure chaos? How do you measure the disorderliness? So S is related to energy enthalpy as Q by T. Okay, so Q is the amount of energy. So where this comes from is basically, imagine a situation. Okay. So let's say there is an isothermal reversible process. Okay, so let's say there is a system, there is a process happening like isothermal reversible process. Let's say like the system that we are considering, it absorbs Q amount of energy from the surroundings. So basically, system has gained plus Q amount of energy. The surroundings have lost that same amount of energy. And because it is isothermal, the temperature remains constant. Whatever heat energy it has absorbed has been used in changing the pressure volume component of the system. Okay, so temperature is remaining constant. Internal energy, there's no change. Only the PV part of it is changed. That we don't have to worry about. So from the point of view of the system, okay, so from the point of view of system, it has gained Q amount of energy. So entropy S, like the change in entropy is defined as, so delta S is equal to positive Q, like the system that, like the heat energy that the system has absorbed upon temperature. So this is delta S of the system. Okay. So if you look at it from the point of view of the surroundings, so this is for a reversible process that we are looking at. Okay. From the point of view of the surroundings, So that overall entropy change in the surroundings is going to be, surroundings have lost that much amount of heat energy. So this is going to be minus delta Q upon T. So the overall entropy change, so delta S total, is going to be plus Q upon T minus Q upon T, that is equal to 0. So this is for a reversible process, something that, again, do you guys remember what we defined as reversible process when we were looking at, when we are getting the expression for the work done?
That which could
Yes,
come back
ma'am.
to original state. When you do it like by little, then you can just reverse it.
Yeah. Okay. So it's something that you are constantly controlling. That is the case. Now, when we consider an irreversible process, which a lot of like spontaneous processes tend to be, so when we consider an irreversible process, reversible process may, you are like it's going step by step. There is an infinitesimal change in the what do you call, volume, because then the temperature will remain the same. In an irreversible process, let's say, then we have to look at the temperature changes also that accompany it. So in this case, let's say system is at temperature T1 and surrounding is at temperature T2. So again, the same situation where system is absorbing heat energy, like Q amount of energy from the surroundings. So, okay, so system is at temperature T1 and surroundings is at temperature T2. Okay.
Man, I didn't get the point. How does it really, take in the energy from the surrounding? It could also give out, right?
It could. We are making an assumption, like in this particular case, that let's say there is Q amount of heat absorbed from surroundings to the system. And it's pretty simple. Like if it was the opposite, then Q would be a negative value. If I say like minus 100 joules was absorbed, it means that it just went in the reverse direction. Plus 100 joules was actually given out. All right. Now let's look at the entropy changes in this situation. So delta S of the system is equal to, it absorbed Q amount of energy. So this is going to be plus Q upon T1 because the system is at T1 temperature. And the delta S of the surroundings is equal to minus Q upon T2 because it lost Q amount of energy from the surroundings. So let's look at what happens to the total entropy change. So delta S total will be equal to plus Q by T1 minus Q by T2. So now, Rishit, we look at the point that you brought up. I'll take Q common. So I'll get 1 by T1 minus 1 by T2. So this is the overall change in entropy in this situation. Okay. Case 1, if system was at a higher temperature, if T1 is greater than T2, what direction would the heat energy like change be in? Like Q will be positive or negative?
Negative.
Negative.
Negative. The system will tend to lose energy, right? So Q ka value is going to be negative. So delta S total will be equal to Q will be a negative value multiplied by, if T1 is greater than T2, what will be this whole thing? Will you get a positive value or a negative value?
Positive.
Positive value.
Think again.
Negative.
Value.
If T1 is
Negative.
greater,
Sorry.
So T1 is
T1
greater.
is greater, right?
So
Then
if
negative.
T1 is greater than T2, if you compare 1 by T1 and 1 by T2, which one will be greater?
One by T2.
1 by T2.
Sign reverse.
oh, okay.
ना? So 1 by T1 is less than 1 by T2. मतलब इसको subtract करने पे what value will you get?
Negative.
Again,
Negative.
So overall in this situation, delta S total happens to be a positive value, which means delta S total is greater than 0. So let's take the opposite case. Case 2, when T2 is greater than T1. So system is at a lower temperature. In this case, what will happen to the delta S total? If T2 is greater temperature than T1, system is colder, then Q का value क्या हो जाएगा? The heat absorbed.
Positive.
Positive.
Here it will be positive.
Positive, because this is at a higher temperature. It will, like, the direction is going to be towards the system heat energy. So Q will end up being a positive value. So this is a positive value multiplied by, what will happen to this when T2 is greater than T1?
It's positive.
Also positive.
Positive value.
Positive. So when this iska opposite hi hai na, so when you do the math, this is going to be a positive value into positive value. So overall ends up being a positive value again, which means delta S total is again greater than 0. So overall, always, whenever you have a change, whether the system is losing heat or gaining heat, whatever happens, the entropy will always remain like a positive value in the case of an irreversible process.
Ma'am, can you go back to the reversible process wala slide?
Huh.
Give me a second. I need to copy the last two things.
Okay, sure. So basically what we proved is whether it's a reversible process or an irreversible process, delta S happens to be either 0 or a positive value. It can never be a negative value, meaning you cannot have entropy decreasing. Either it will remain constant or it will increase only. So especially in a spontaneous process, it always ends up increasing. Like that's what irreversible processes are. It'll always move forward. Reversible, even if you try to control it at every step, 0 ho sakta hai, lekin it can never be less than 0. Delta S is always positive.
Could you go back one more slide?
This one, second law. You didn't note this down?
Okay. No, I noted it. I thought I missed out one thing. Could just go back to yeah.
Ma'am,
Hmm?
why do we divide Q and T?
That is how you would measure entropy. So it is energy divided by temperature. That's the mathematical listing.
You can go to the next slide.
Again, go to that slide.
Okay, reversible. So once you're done, let me know. Go to the next one. So once you're all noted down, done with this, then we'll move on to Gibbs energy.
Done, ma'am.
Yeah, what's up?
Actually, I had a doubt regarding like the perpetual machine motion, like motion machine basically.
Huh.
Like like
Could you go
doesn't
back?
it like in like we know like an arc reactor in Marvel, like Iron Man has an arc reactor now. Like it basically like doesn't require any external energy. So won't that ulta contradict the thermodynamic laws in that
Yeah,
sense?
that's why you
Because
can't have it in real life. And secondly, Iron Man's reactor, I think he has a radioactive energy source.
yeah, and that is period. He made a new element in Iron Man 2, but then uske baad, when he like, started using nanotechnology, so he
Hmm.
stopped using any external
I think
powers.
what I had canon, or it's not like I follow it so much, but what I understood of it, I think he designed it in a way where you won't need to like change batteries immediately. So I think he's designed it in such a way that the energy source lasts for his lifetime, or at least the suit's lifetime, basically.
Yeah, yeah. It was something like that. Like he used the battery when he was creating it in that cave prison wala thing na.
Hmm.
So I think he created it so that it would last him till like a very long time.
Yeah.
But I think he disregarded that design because later on he got many more different suits now.
Hmm. Yeah. Could be. But yeah, he wasn't like reusing, like recycling the energy. He was just using a battery source that's just gonna last for a pretty long time.
Could you go to the next slide?
Yeah.
So in a reversible process, we can't have the entropy as more than zero.
No. Always zero. Wait. Reversible process, na? Again, we took the case of a reversible isothermal process. Uh, Even if it was not isothermal, adiabatic matlab energy change is zero, so overall will become zero. In this specific case, like reversible isothermal or reversible adiabatic process may, it will always be zero. But if you're like changing the quantity of the but delta is total consider kar rahe na? Yeah, it's always going to be zero only. System plus surroundings overall is always going to be zero. Generally, energy upon temperature is the thing for entropy. Like यहाँ पे, because there was a change in heat energy where we are adding heat energy or removing heat energy, we took Q by T. Depending on the situation, like for example, if you're considering uh, reaction taking place, then it's going to be delta H reaction upon T. If you're considering phase transformation, vaporization, then it's going to be delta H vaporization upon T. So it's the energy change divided by temperature is what you will like, what gives you the entropy change value.
Ma'am, could you just explain it once more? What did you write about the delta's total one? How did you get both of them as negative?
So delta is total, like universe ka entropy change consider kar. So universe is made up of system and surroundings, everything around it, right? So if I'm looking at the overall entropy change in the universe, so this is basically equal to, oh, I haven't written it here, that's why. So delta S total is delta S within the system plus the delta S within the surroundings. So I'm just adding them up both together, in both the cases. So S total is basically like entropy change in the universe is equal to entropy change in the system plus the surroundings.
So it's basically Q by T1 minus Q by T2 plus q by T1 plus minus q by T2 of surrounding and system.
So system is Q by T1 plus Q by T1, and then surroundings is minus Q by T2. So I just added both of them.
Ma'am,
Hmm?
can we say that the formula for entropy is energy upon temperature?
Yes. Energy, enthalpy, like depending on the situation. Yeah. Essentially, it's energy upon temperature. So units of entropy is joules per Kelvin. Actually, just let me know when you guys are done till here, huh? Just like give a thumbs up or something. Yeah. Okay, so Sanskriti and Kaveri and Sanat, once you guys are done, Sanskriti is done. Okay.
Oh, I did the reaction.
Reaction?
Like thumbs up wala reaction.
Okay, missed out. Okay.
Ma'am, just a second.
Oh, you okay. Sanskriti is done. Yeah, okay.
Ma'am, I searched on Google about that arc reactor thing which we were talking about.
Mm-hmm.
It says that Iron Man's reactor is essentially a fusion reactor
Mm-hmm.
that harnesses energy by removing electrons from hydrogen atoms. This removal of electrons creates an ion plasma, which is the ultimate source of energy.
Okay.
कुछ समझ नहीं आया but सुन के अच्छा लगा.
Same.
I don't get it. It's not a fusion reaction. Maybe it's trying to imitate a fusion reaction, but like it's either creating that ion plasma or it's a fusion reaction. It can't be both at the same time.
But if you remove the electron from hydrogen,
Mm.
then the hydrogen would become, would become.
That would be a fission
can't
reaction.
say. Yeah.
It's not fission or fusion. As Ritu says, absolutely. That's pop culture thermodynamics. Yeah. Fission is when you're breaking apart an atom and then you're creating new substances out of it. Like uranium breaks apart to give you polonium and neutron, something like polonium plus beryllium plus neutron, something like that. Fusion is when two atoms join together to create a completely new atom. Like two hydrogen atoms join together to, like, I think a hydrogen plus deuterium joins together to create helium. So that's fusion. What the process Sanati just described is just like you're taking hydrogen beyond boiling point and you're breaking apart the atom to create plasma. Move electrons, you get like a mess of energy and whatever random matter, protons, electrons, that is plasma. Absolutely, that makes sense. But yeah, it is pop culture thermodynamics. The whole thing does not make sense.
Yeah, it's just a movie. We don't need to dwell into the physics of it, physics or chemistry.
You can continue. Okay.
Okay, so now let's talk about Gibbs energy. All right, so Gibbs
Just
energy.
a small doubt.
Uh-huh.
If they do take out the atom or the electron from hydrogen, what does happen? What happens to hydrogen?
It just exists as a proton and an electron, a gooey mess of a proton and an electron. Like that's basically what stars are made of. So that it's just recreating a star there. That's it. Right. Coming back to this Gibbs energy. So the formal definition for Gibbs energy. Now Gibbs energy is something, again, we're bringing it back to chemistry. it is the most relevant in the context of chemical reactions and all that. So if you want to figure out, be it an exothermic reaction, endothermic reaction, whatever kind of process it is, if you want to figure out if it is feasible or not feasible, you are going to look at only the Gibbs energy factor of it. Okay. The definition is, so like earlier textbooks, you may also see it called as Gibbs free energy. It is also referred to as just free energy. And as the word says, free energy hai na? So it's basically the maximum amount of energy that is available to a system that can be converted into useful work. That's like the formal definition of it. But mathematically, Gibbs energy denoted by G. So G is basically equal to H minus Ts. Okay. So why it makes sense? So whatever energy is going into increasing the entropy of the universe, so that's not useful work because that's going into the entropy. It's not being invested or used for the process. Enthalpy of a reaction or any particular process, that's something that's either released or absorbed during a process. This is relevant to the process. So total Gibbs energy, iska mathematical formula is H minus Ts. This is important. This is what you'll be using in your numericals and calculations everywhere. So in a particular process, again, Gibbs energy, just like enthalpy and entropy, G is an extensive function. It is a state function. Because enthalpy is a state function, entropy is a state function, temperature is a state function. So Gibbs energy of a system is also state function. Okay. So when any process happens, if you want to calculate delta G, change in Gibbs energy, that is equal to delta H. Delta H is the same delta H, your change in enthalpy you've been using throughout, ionization, atomization, bond dissociation, whatever it may be, minus T delta S. Okay. Now this particular value, Gibbs energy, because it takes into account both the enthalpy change as well as entropy change, this will give you the correct picture of how you can figure out the feasibility of a process. Now, unlike exothermic endothermic reactions, with delta G, it is pretty straightforward. If delta G is less than 0, any process will happen. So in scientific terms, we call it the reaction or the process is feasible. And if delta G is a positive value, is greater than 0, it will never happen. Clear?
Never happen as in like on its own, right?
On its own, and otherwise, like
if we add a catalyst to it, then it would happen, right? Or like if we add energy to it.
You need to keep adding energy, yes.
Like we need to keep the favorable conditions constant for it.
Yeah. So
But now if you add energy, won't the delta H change? So then technically like delta G would also change.
yeah. So that is why we just classify it as spontaneous. If it is greater than 0, it is not spontaneous. And if delta G is equal to 0, Rishi is asking what will not happen or happen, like that particular process we are talking about. If we are talking about a reaction, then that reaction being spontaneous, non-spontaneous. Delta G. So non-spontaneous reactions are very, like, here we talk about, oh, we need to spend energy for it and all. But when, if at all we come across a situation where theoretically delta G is greater than 0, it is not economically feasible also to keep giving that amount of energy. So practically speaking, if it is non-spontaneous, we won't even look at it, like we won't considering making it happen that way. So that's why it becomes quite important. We will only consider for, if you want to manufacture anything, if you want to look at the chemical properties of anything, like if you are looking at a specific reaction, you're studying about it, delta G is always less than 0. Like those are the kind of processes that we care about, practically speaking. If it's greater than 0, we don't really, that's why I called it as it won't happen. And when delta G is equal to 0, it is in equilibrium state. Equilibrium matlab, like both the forward process, reverse process, both of them are happening at together. It's like basically balanced. That's equilibrium. Definition, I'll give you guys the statement. So Gibbs energy or free energy is the maximum amount of energy. So the maximum amount of energy that is available to a system during a process that can be converted into useful work. So that's available during a process. Process basically means any change, like it could be a chemical reaction, it could be a phase transformation, it could even be something as simple as diffusion. So that can be converted into useful work. Okay. So again, just like with enthalpy, delta G, this is like the most roughest thing. If you're considering free energy in standard state, it's represented by delta G naught. So this is at standard state. That is 1 atmosphere pressure at a specific temperature, all of that.
Ma'am,
Hmm?
so we did like thermodynamics ka revision in our class, I think yesterday
Mhm.
or day before, and our ma'am gave us some questions as a test.
Okay.
But like we didn't have ample time, so I was only able to do the first 2. So can we do those also after we're done with the chapter?
We can look at a few questions because it's 3:30, right?
It's only like 4. It's only like 4 questions.
Oh, okay. Yeah, let's look at
Yeah.
that.
I'll send the
I'm
pictures
like
on
the second sum is like direct formula, so it will not take more than 1 minute. Third and fourth can take. Fourth is about Gibbs energy only.
Yeah, like the third and fourth have log in them, and we weren't taught log very well.
Okay. What? Yeah, we'll look at it. Like I intended to look at some questions. I was looking at example questions, but yeah, that works. Share, like if it's given in a doc or however it is, just share it somehow and then we'll
Click pictures of it.
Yeah.
I'll send those. Then I'll try looking for this thing also, Google Classroom if it's there. That'll be much clearer.
No, Sanath, it's not there. Not been posted yet.
Okay, then I'll just send the pictures I clicked.
Oh,
Could you again explain the point about that max amount of energy? Can you explain that point again?
It's just the definition of Gibbs energy. Like what it means is It is the maximum amount of energy that is available to a system. Like for example, let's say our system is ye wala beaker in which there is some reaction happening, like reaction is supposed to happen. So Gibbs energy is what is the maximum amount of energy that is available to that system during a process, during that particular reaction while it is taking place, that can be converted into useful work. So useful work is something like the amount of energy that goes into what do you call, making that process happen. Kaveri is asking, does that energy have to be provided by the surrounding? Absolutely. Like system and surrounding, like if the system doesn't have sufficient energy, it's going to absorb it from the surrounding only. So when you are igniting a paper or something like that, that's essentially heat energy coming in from the surrounding. So even evaporation of water, if we focus on the specific molecule on the surface that's about to evaporate, it's taking in energy from the surroundings only, from the other molecules, transfer of kinetic energy as it collides with other molecules. So yeah. Universe, like if you're doing thermodynamics, there's only two parts to a universe. One is the system, which is like whatever you're focusing on, and everything around it is the surroundings. So agar system mein nahi hai, to surrounding se hi aayega. Yeah. Okay. So useful work is whatever like is happening into the system, something that's not being, I don't want to call it wasted, but something, like you have some loss of energy as in the form of radiation. Like heat energy is always radiated. Conduction, convection, it depends on, if there is a conducting material there. Convection ke liye, you need to have those moving molecules there. Even if you don't have both of these, radiation always happens. It's always spontaneous.
I still don't get what the useful work is.
That's what useful work is. Something that's going into like work done by the system, something that's just not lost in the form of radiated heat energy or something or the other, something that's going into the process that the system is doing, be it expansion, be it that particular chemical reaction, whatever it may be. If it is not going into other random things, like the most obvious thing I can think of is just the radiated heat energy. Heat energy, like if you have energy in the form of heat, it will always be radiated, like some amount of it will always be radiated. Like that's what you feel as the warmth of a fire or whatever it is. So. Another point, like this particular equation, delta G equal to delta H minus T delta S, this is called Gibbs-Helmholtz equation. This particular equation. Or just the free energy equation, Gibbs equation. Ritu is asking, is fire just an energy disturbance in the visible region? Visible and invisible region. Like heat is, again, infrared is mainly heat energy. You can't see it, but you can feel it. And you are going to have like energy wavelengths outside of it also, like electromagnetic radiation. That's what radiation is.
It's just like a disturbance.
Yeah, it is energy disturbance. Plus you do have matter in it as well, which is where your color of the flame comes from. So depending on what you're burning, like natural gas, methane, and all, you have a blue flame because the atoms, molecules involved in that particular combustion impart that particular color. If you have wax, you get like a yellowish orangish flame. If you have some metal ions, that's where your flame test comes from. You have all these colorful flames in a firecracker. So it's energy disturbance plus some amount of matter in gaseous form, and you might have a little bit of plasma there as well. It's like a whole mess of things, mixture of things.
Ma'am, I sent the questions on the group.
Oh, okay. So this is how you took the questions. Okay.
Yeah, ma'am gave it as like a 10-marker test.
Mm-hmm. I'll just download it and I'll see if check it here. WhatsApp. Oh, nice. It's clear, quite clear. You guys can see it?
Yes, ma'am.
Okay. So calculate the enthalpy of formation of methane from this data. These are the kind of questions you get in thermodynamics. Told you, like, focus more on the enthalpies. Second is also delta R H naught only from the given thing. Okay. So do you guys remember what is enthalpy of formation definition?
Formed from the constituent elements, the reactant, the product side has to be 1 mole.
So basically enthalpy of formation. So you're given CO2, CH4, H2O. What reaction what equation do you think? Oh, you're given delta HC. What does this value stand for?
Enthalpy of combustion.
Enthalpy of combustion.
So what equation do you think associates all of the given compounds?
C plus H is like gives CH4 wala.
But you
Do
don't
we
have
have to write question or like?
see, when you have enthalpy of combustion, what equation gives you the enthalpy of
CH4 plus O2, right?
correct? So you start from that equation. CH4 plus O2 gives CO2 plus H2. Now, when we say enthalpy of combustion, are there any specific criteria for combustion? Like definition mein? Because all of these in gaseous state only. Again, all of this will be in standard state, matlab water will be in liquid state because that is standard state. Guys, at least like flip your notes and tell me what is heat enthalpy of combustion.
1 mole is burnt completely in oxygen and all reactants and products are in standard state.
Correct. So standard state में होना चाहिए 1 mole of methane होना चाहिए. Balance the rest of the equation in order to like suit it this. So balance करने पे क्या मिलेगा?
You put a 2 on O2.
2 on O2, okay.
And a 2 on H2O.
And 2 on H2.
Correct. So now, what would be the mathematical equation? Like delta HC of CH4 will be equal to, how would you calculate the delta HC of CH4?
It's
We break
given
down CH4.
minus 890.
Products minus reactant. So it's basically same as enthalpy of a reaction only, but in specific condition. Ki this particular substance should be burnt in oxygen and you should burn 1 mole of it. So,
But it's given to us.
yeah. So
Yeah,
delta
it's given there.
reactant minus products minus reactant. So that's sigma, like add all the heats of formation. So this will be heat of formation of CO2 plus 2 moles of H2O formed this equation. So 2 into delta F heat of formation of H2O minus the reactant side में oxygen का heat of formation, what will it be? It's not given here. So what do you take it as?
We can use the CO2 equation.
Not necessary. You guys, what did we talk about when we said heat of formation? If something is in the elemental state and in its standard form, it's going to be 0. Because elements exist, right? Like you don't have to form them separately like you would with compounds. Elements ke liye, whenever you have pure elements, H2, O2, C, graphite, F2, Cl2, Na, K, solids, like all of that, it's going to be 0. So oxygen ka heat of formation is 0. Wherever you find something in the elemental state, you can take it as 0. Agar compound nahi hai, matlab, take it as 0. So on the reactant side, you only need to consider the heat of formation of methane.
I didn't understand oxygen ka element.
What is oxygen? Is it an element or a compound?
Compound.
What?
It's an element.
O2. I said O2 is not.
O2 is still made up of only oxygen atoms, right?
Like a molecule.
It's a molecule, yes. Molecule of an element. So the fundamental difference between elements and compounds is compounds are made of molecules of different substances like CO2, H2O and all. Like if you want to get CO2, you need to have carbon and oxygen. If you want to get table salt, NaCl, you need to have sodium and chlorine. So oxygen is made up of oxygen only. So that would be an element. There's a difference between compounds versus molecules. Molecules are made up of multiple atoms, can be the same, can be different, but you will have molecules of compounds versus molecules of elements. So if they're made up of different elements, then they are compounds. Whether they're made up of same element, like whether it's a molecule or an atom, as long as you have a single element, it's still an element. It's just oxygen. Okay, so that was the fundamental this thing why you were confused, I guess.
Ma'am,
Yeah.
you wrote delta H product minus its reaction, right?
Reactants.
Then, yeah, reactant. So, why did you change it to formation? Couldn't you? I don't. How did you exactly do
Delta
this?
H, these are heats of formation that I'm talking about. Go back and revise when we were talking about enthalpy of a reaction. It's always the enthalpy of formation that we talk about.
The reaction part could be any, like, could be formation or combustion. You can use this formula, right? I think there is only one exception to this.
No, like generally for any equation, any chemical reaction, enthalpy of a reaction is enthalpy of formation of the products minus enthalpy of the formation of the reactants. So for enthalpy of formation, that's a special case because this we defined it as when that compound was formed from its elements. And elements, we define delta F to be 0. So in that case, enthalpy of formation of the reaction is automatically equal to the enthalpy of the reaction itself. So that way. But every other reaction, if you look at combustion, it is enthalpy of a reaction only, but a very special case of a reaction where that reaction happens to be combustion. So we put some conditions on it कि combustion मतलब oxygen के साथ ही reaction होना चाहिए. Also we said that we are combusting 1 mole of the substance so that you don't take any random value of it. So you change the equation as per those criteria and the formula still remains the same. So to that modified equation, you apply the formula, enthalpy of formation of the products minus the enthalpy of formation of the reactants. Okay, so here enthalpy of combustion is known, it's given. CO2 is known, given. H2O is also known, given. This is an unknown, this is what we need to find. So you just plug the values. Be careful, if negative values are there, you need to put it as it is. So iska calculation hoga minus 890 equal to, another thing you need to be careful is all of them are kilojoules per mole. Agar ek bhi joules hota na, you need to do that conversion plus into 1000 or divided by 1000. CO2 is minus 393.5 plus 2 into minus 285.8 minus, we don't know what this is, X. So just solve for X and you'll get the heat of formation of methane.
Ma'am,
Yeah,
briefly go over the steps again.
yeah. How many of you have followed this? How many of you have a doubt?
So like in school, we did a different method.
How did
So
you do
ma'am
it?
told us to like use the different like either enthalpies ke values are given. No? So she told us to make like equations from those values. Like if there's a delta FH of CO2, then we'll make the equation ki C plus O2 is equal to CO2. And then like we'll write the enthalpy beside it. And then same for the other enthalpies. And then after that, we'll try to constitute an equation of all the of all the elements to get the equation for formation enthalpy of CH4.
Which is this?
And then like that, yeah.
You follow that, you'll end up right here. So that's like a longer.
No, ma'am.
very-
So what you are saying is combustion. We need to do it for formation. That's what ma'am told. We need to get the formation
to
equation.
combustion, because here this value that is given is enthalpy of combustion. So eventually the reaction that you take should be a combustion reaction of this. Here it just fell into place very nicely, so it doesn't make a difference. But if you are like, if you come across a equation where you have like 2 moles of CH4 plus whatever moles of oxygen gives something CO2 something H2O, then your calculation will be wrong, because if you are considering an equation with 2 moles of CH4, then it won't be enthalpy of combustion anymore. You can't take this value. So that is going to be a little more confusing, I would say. This is pretty straightforward because you're directly looking at what values you're taking. So heat of formation hai, theek hai. Enthalpy of combustion hai, and you know that enthalpy of combustion only applies to a specific case of a reaction. So write that reaction, which is what I've done here, combustion of methane, to see that all the conditions are fulfilled so that whatever I calculate here should be the enthalpy of combustion. Then I plug in the necessary values. Okay, this is easier and much more straightforward, and it is completely going by the definition of all the different enthalpies that you've learned instead of trying to construct it completely. So even this reaction is also pretty straightforward, and that's exactly what you'd be doing. So H2 gas plus Br2 gas gives 2HBr. You're given bond enthalpies. So think of it logically. In order to create HBr, you first need to break HH bond, and you need to break Br-Br bond, and then you need to form the HBr bond. So delta HR is going to be 2 into HBr minus the HH and minus the Br-Br.
This was like direct application of the formula, right?
Yeah.
I have a doubt. So for the first one, when you do the X, like what does the X signify? Like what do you get if you find the value of X?
I assume the unknown to be X. Like I don't have delta F heat enthalpy of formation of CH4, so I took that as X. Instead of X, I can just write delta F H CH4. This is the value that I get.
We can do it directly also like this.
Yeah. Same thing, Rishit.
Okay.
I just took it as X. That's it.
Like as Sanat told, our ma'am did it in the other way. Can we also just directly do it with this formula? Because some people were saying, ma'am, you can just directly use the formula. Ma'am was saying when the NCRT it is given with the steps, so you actually do that. That's why.
Do one thing. If you're given this question for like 3 mark or 5 mark or something, then they're probably expecting the step marking. So write down all of the equations of the formation of like H2O, CO2, CH4 and all that also, and then do it. But if you're asked for like 1 or 2 marks, then you can directly straight away just do this. It's sufficient.
I think there was like a similar question in the NCRT based on C6H6.
Mm-hmm.
Yeah, so in that they showed the proper steps and all.
I'll tell you what the logic for that is. It's going to take really long. So we have CH4, CO2 and H2O, right? Okay. Heat of formation oxygen भी है, but इसका 0 होगा, delta H heat of formation. Ritu, yeah, seems to be correct. Like Smera also got that. So guys, is the answer minus 75.1 kilojoules per mole? If you've done it in class, compare it. I'll write it here.
Yes, ma'am, minus 75 point.
Sanat, Rishit, Kaveri, like since you guys have done this in class, this is a value we got.
This is for the first one.
It should be, I think it should be positive.
No.
Wait.
Heat of formation.
Oh, wait, no, it'll be negative.
Yeah. Okay,
I
I'll tell you
forgot to put
what
this
the
in.
logic is.
Yeah, this is the one. The value.
Then C plus, sorry, writing here 4H. C plus O2 gives CO2. The value you get is delta heat of formation of CO2. And then H2 plus O2, half O2 gives H2O. So this is heat of formation H2O. Okay, so you have all of these. And yeah.
Wouldn't it be heat of combustion for the second one?
Again, I told you, right? I'm creating 1 mole of CO2, like whatever is the enthalpy of change in this particular reaction, if all my criteria are met, then you, like it's going to be the same. So if I'm looking at it from the point of view of I'm burning 1 mole of carbon, then it's going to be heat of combustion. If I look at it as from the point of view that I'm creating 1 mole of carbon dioxide, it becomes heat of formation of carbon dioxide. Okay. So if you compare numerical values, they end up being the same anyway. So it's the context that matters. So how do I connect all these three? These three compounds can be connected by combustion of methane. You have CH4 plus, what was that? 2 oxygen gives CO2 plus 2H2O, right? Now, if I look at it, this particular equation, it could be random enthalpy of reaction also, but also happens to be the fact that I am burning 1 mole of methane in oxygen, which means the heat of the reaction for this has become heat of combustion of methane. So then you manipulate these 4 equations. So how do I get this equation from these 3 is मीथेन तो LHS में होना चाहिए. So I reverse this equation, and these two are in RHS, so these two I'll take it as it is. So if I take minus of this and I add them up, I essentially get this particular equation. So like that's how the mathematics matches up.
Yeah, this is how we did it.
Yeah. So if
And
I
like
do
we
this,
replace the
and, yeah.
enthalpies.
So if I do this and eventually if I land up at, like whatever final equation that I get, delta HC combustion of methane equal to this value plus this value minus this value, like whatever I do, if I like the final equation that I get, if you compare it, it's going to be the same thing mathematically. So this is, I would say, a longer method of doing it, because essentially my enthalpy of a reaction, whether it's for combustion, whether it's for formation, any sort of reaction I take, it is sum of the enthalpies of formation of the product minus the sum of the enthalpies of formation of the reactants. When I know this concept already, I'm just applying it directly instead of splitting this as to why did I get product minus reactant. Why do I have product minus reactant? This is where it comes from. Because essentially elements ke liye, it's all going to be 0 anyway. So these all won't count. So what I'll be left with is just enthalpy of formation of these particular compounds. Yeah. Just a moment, guys. I'll just